In the previous video, we already introduced standing waves, but we made no assumptions about the length of the string. But for most string instruments, such as a piano, a guitar, a violin, the strings have a finite length, and they are fixed on both ends, on both sides of the string. And so in this video, we will show that there is a fundamental frequency, f1, which is equal to v divided by 2L, where v is the wave speed. Remember that v is equal to the square root of t over mu, where t is the tension of the string in Newton, and mu is the mass per unit length of string in kilogram per meters. And L is the length of the string. Last time, we saw that the nodes are separated by lambda over 2. Now, if you don't remember this, I urge you to watch the previous video again, because I will assume that you know this here. So we consider now the fact that the string is fixed on both sides. So this means that there must be a node at both ends. So the length of the string has to be a multiple of lambda over 2. So we can write L equal n lambda over 2, where n is going to be an integer number equal to 1, 2, 3, and so on. You can see that there are only few standing waves that can satisfy this, and those are the standing waves for which the lambda is equal to 2L over n. And since the wave speed is equal to lambda f, several wavelengths lambda will give me several frequencies f. So f will be equal to v over lambda, and so that will give me f is equal to nv over 2L. And this is the formula I wanted to derive. So you see that the only important concept for this derivation is that there are nodes on both sides and that the nodes are separated by lambda over 2. Now let's look at a couple of solutions. For n equal 1, we have f1 is equal to v over 2L. And this is called the first harmonic or the fundamental frequency. And it corresponds to the case where we have two nodes on both ends and one antinode in the middle. For n equal 2, we have f2 equal v over L, and this is called the second harmonic. And if you are a musician, you may call this the first overtone. It corresponds to the case where we have two nodes on both ends and one node in the middle, and two antinodes at 1/4 and at 3/4. 3/4 of the length of the string. For n equals 3, we have f3 is equal to 3v over 2L, and this is called the third harmonic or the second overtone. And it corresponds to the case where we have four nodes, one at 0, at 1/3, at 2/3, and at the end, and three antinodes, which will be at 1/6, 1/2, and 5/6 of the length of the string. Now let's see if I can reproduce these normal modes on the rubber hose. So here is the fundamental frequency with two nodes on both ends and one antinode in the center. Okay, let's do the second harmonic. Here you go. You can see one node at the center and two antinodes. All right, then let's try to do the third harmonic. This time we can see three antinodes. How about the fourth harmonic? Here you go. Not bad. Okay, I can see 4. How about 5? Can I do 5? Let's see if I can do the fifth harmonic. Oh yeah, I can see 5. Oh, so great, impressive. Okay, so now how about the torsion wave? Can I do normal modes on the torsion wave? The wave speed on the torsion wave is smaller than the wave speed on the rubber hose, so it should be lower frequency, and so it should be easier. Oh yeah, it's much easier indeed. You can see the standing waves here. So now, which harmonic is that? Okay, I'm going to let you count and let you know, you can let me know when you figure it out, right? Which harmonic is it that I'm doing right now. Now, let's look at this formula again. The frequency f is v over 2L, where L is the length of the string. You see that the frequency is inversely proportional to the length. So a long string will have a lower frequency and a short string will have a higher frequency. And that is why the bass has much longer strings compared with the violin, for example. Also, note that because it is an inverse function, the variation of the frequency with the length of the string is not going to be linear, right? And this is why, for example, the frets on a guitar are not evenly spaced because it's not linear, it's an inverse function, right? The frequency varies with 1 over L. You can also replace the wave speed v in the formula by square root of t over mu, where t is the tension of the string and mu is the mass per unit length of the string. And so this explains why you need to increase the tension to raise the pitch on the string instruments. You can also change the frequency by changing the mass per unit length. And this explains why on a steel guitar, for example, the lower notes, lower frequencies, will have thicker strings compared to the higher notes.